All right, I've got time. So, just a raise of hands. Is anybody here joining for just part 2? Okay, so that is like 40% of the room. So luckily, welcome to part 2 of Algorithm Tuition. My name's Connor. I have put together a 3-minute summary of the first part of the talk. Luckily, you don't actually have to have seen the first part, but just so that if I'm making references back, you'll sort of know where we came from. So first of all, part 1 summary in 3 minutes. Scott Schur said the following.
I'm not an expert, I'm just a dude.
That applies to me, and he also said that you get chocolates if you answer or ask questions. I believe my trusty volunteer, who's somewhere in the crowd, should have some chocolates left, so if you answer or ask questions in the midst of this, make sure to get your chocolate. Then Sean said,
that's a rotate.
And then he also said,
so you have all these algorithms at your disposal, right? Learn them. It's very important.
And that caused Marshall, Kate, John, and Odin to say,
is using standard algorithms.
Because he knows the algorithms.
We need to know all the STL algorithms.
I should go look in algorithm.
Learn your algorithms.
And all of these statements combined with the fact that we want to write.
And just as you can say, that would be a good use of a linked list, we don't have that intuition about algorithms yet, and we need to.
And sorry, and all of those statements combined with the fact that we want to write
beautiful code.
Brings us to this talk, which is to hopefully develop algorithm intuition. So the goal for you, which was covered a little bit in part 1 and now continued in part 2, is to get you excited about algorithms, to learn a new algorithm, and to start to develop some algorithm intuition. So we started off after watching those clips in part 1 by looking at a simple question where we went through multiple different solutions to solve the problem of finding the difference between the minimum and maximum element in a list. This was the final code that we got to, which utilizes C++17's class template argument deduction and structure bindings, along with C++20's range-based version of min-max elements. So this makes me extremely happy. Then we talked about how there are 111 algorithms across the algorithm, numeric, and memory headers. And in this talk, we are focusing on the algorithms in the numeric header, which there are 11 of. The first one we covered was iota, which is used to generate a sequence of numbers provided an initial value. We also covered iota shaming. If you're interested in this and you didn't watch part 1, go check that out on YouTube. We then moved on to accumulate and reduce, which are 2 extremely important algorithms. We took a look at the Wikipedia page, which talks about how this algorithm is known as many different things in many different languages: fold, reduce, accumulate, aggregate, compress, and inject. And we also talked about how in category theory this is referred to as what's called a catamorphism, basically taking a list of elements and shooping it down into a single element. We then took a look at what this is called in Rust, which is fold, and then we then took a look at what it's called in D, which is both fold and reduce. And then we took a look at a bunch of different algorithms that can be implemented in terms of this sort of stood, accumulate, reduce, / fold algorithm. And we also then went to Ben Dean, who said the following.
I was able to implement all of them in terms of accumulate.
All of them is not actually all of them, because this is a short and clipped. It was 77 of the 90 pre-C++17 algorithms in the algorithm header. So go check out Ben's talk. It's a fantastic talk. And it just shows how you can utilize these fold operations, stood accumulate, stood reduce, to implement many of the other algorithms in our algorithm header. We then took a look at our 4th algorithm, adjacent difference, which we motivated by taking a look at this example, which the simplified version is find the minimum difference between 2 values in a list. We took a look at 2 solutions ultimately. One of them was by sorting, then taking the adjacent difference, which calculates the difference between the adjacent elements, and then by taking the minimum of the values from that difference list. And then finally, we took a look at the catamorphic version of this that doesn't allocate linear memory. But then we actually had extra time, so we went on to cover a couple extra things, which we're going to quickly skip through. And I'll highlight those for those that are joining for the second part. So these were the 4 that we initially talked about. We then covered a hacker egg example that basically was a motivation for stood inner product. So basically, we have zip here in the Python solution that we don't currently have in C++ 17 or 20, but it is coming. But in the meantime, by taking a look at some of these slides, we get to this, which is stood inner product, which is an algorithm for basically transforming values from two different lists and then using another binary operation to reduce those transformed values. And then we took a look at some slides from Matt's talk, which we're not going to go over, and Matt said something interesting, and then we found that we have a renamed version of this algorithm, inner product, which is transform reduce. So transform reduce, it's my favorite algorithm. It makes me extremely happy. And then we covered some motivating examples for using this. So basically, the default operations that come with transform reduce are plus and multiplies, but we can override those. And then I made a final comment right before the break, was that I thought that transform reduce maybe wasn't the best name for this algorithm. Why not call it zip reduce? But that's because transform reduce doesn't have to zip. There is an overloaded version of this that basically takes a unary operator right there at the bottom that for the transforming operation only takes a single list and transform those values. So because we don't have to zip, this is the perfect name for this algorithm, transform reduce. And that brought us to this example. So here, I originally, in the original version of this talk, made a completely false statement. And I said that these two lines of code, or two examples, x and y, are identical. And basically so on the second line, we have the transform reduce using the overloaded version that only takes a unary operator for the transformation. So basically what we're doing here is we're attempting to square all the values and then sum them up. The original statement that I made was that I'm not sure actually which of these two pieces of code is better. Because the code in our Lambda body of our first piece of code using std reduce is so simple, it seems like almost overkill to use std transform reduce where we're separating the fold operation from the transform operation. The transform operation is the squaring of the values. The folding operation is the summing of the values. And so I sort of said, I haven't made my mind up. It's which one's better? I'm not sure. Unfortunately, the first one's actually wrong. And only the second one is right. And that was pointed out to me by an individual that people at NVIDIA work with, Mark Harris, who works on parallel algorithms. And he pointed out that the binary operation in the reduce algorithm does not meet the criteria, which I've sort of ignored for the first part of my talk, of commutative and associative. So because you're going to end up potentially squaring intermediate values, this first piece of code is broken. You have to have a binary operation that is both commutative and associative, and this lambda is not. But in the second example, because we've separated the transform operation from the fold operation, we now have parallelizable code. So I kept this slide in here because this was sort of like a very important moment for sort of understanding that reduce is extremely different from accumulate in that accumulate goes from left to right. We don't really need those criteria of associativity and commutativity. And when we run into that problem, that's why we have the transform versions of a lot of the parallel algorithms, which we're going to talk about a little bit later as well. So this is very important. And while we're on the topic of Mark Harris, he also pointed out, which out of all the talks that I've given this talk a few times now at meetups and at other conferences, not a single person has pointed out that this code is broken. And that is that root mean squared takes the sum of the squares and then averages them and then takes the square root. And none of these examples takes the average. You don't divide by n anywhere. So that's a little neat thing that I thought was worth pointing out as well. So missing the n. So let's revisit. This is great. So this is one of my favorite parts of this talk. Let's revisit the adjacent difference reduce question that we looked at. So this was where we left off, where we are trying to find the minimum difference between elements in a list. So can anyone see, I know Mikhail, he sees, because he stated it earlier in part 1, how we can use inner product or transform reduce to solve this? So transform reduce, two binary operations. The last one does the transform, and the first one does the reduce. So in the transform, we're taking the absolute difference from two adjacent elements, and in the reduce operation, we're just taking the minimum. How do we get the adjacent elements? The two data structures, or basically ranges, that we're passing to transform reduce are the first 0 to n minus 1 elements of our range, and then the second to the last elements of our range. So basically, we're passing it two ranges, which are just different subarrays of the same range. One is 0 to n minus 1, and the other one is 1 to n. In functional programming, for any of the FP enthusiasts in the crowd, this is known as zip tail, where you are basically zipping the original list with the tail of the list, where tail means 1 to the last element. So it's basically dropping the first element. That's what tail is. So this is a very common idiom in functional programming, and I think this is the most beautiful solution of all the three solutions we looked at right now. And furthermore, there's an improvement that we can make to this code. Can anyone see it? Marshall Clow. We don't need to sort the list. That is not possible without turning it into a quadratic solution. You still need the property of the sorted list. So anyone else see the improvement? A hint is that we could make use of an STL function object instead of one of our lambdas here. Stood min. So someone in the crowd said we could use stood min. That is actually not correct. In C++11, we added an overload to stood min that takes an initializer list. And so now you can't use stood min in this context because it doesn't know which one it wants, unfortunately. Sorry, and your name? Matt. So Matt has pointed out that because we have a sorted list of elements, we know that the second element in our adjacent pair is always going to be bigger. So we don't have to take the absolute difference. We can swap the 0 to n minus 1 and 1 to n in our two ranges. So you can see there that we initially are taking cbegin and then decrementing cend and then plus plus cbegin. We swap those two, and now we can use stood minus because we always know that the second element is going to be greater. So that's just a small optimization. For me, this is fantastic. Being able to use transform reduce, avoid the linear allocation that we have from our adjacent difference algorithm, and it's my favorite algorithm, so anytime I get to use this, it makes me extremely happy. So in Haskell, question? Yes. So the comment from the crowd was, are the arguments for transform reduce, so the algorithm is named transform reduce, but the lambdas or the binary operations that it takes follow the reduce transform. So the first algorithm is for reducing, the second one is for transform. So yes, it is sort of backwards. I was asked this previously, and I looked into it, and the best answer I have is that they were trying to be consistent with inner product, which then sort of asked, well, why did they do that for inner product? Well, inner product didn't have the semantics of actually mapping the binary operations into the name. So when you were designing an algorithm called inner product, it didn't really matter. And then they just tried to maintain consistency with inner product to avoid the bugs that would be created if you wanted to upgrade inner product to transform reduce. I think that was the motivation for the confusingness of, yes, having the binary operations backwards compared to the algorithm name. So if we take a look at what this looks like in a functional language like Haskell, here it is, and basically we're just composing three different functions together. I prefer to look at composed function code as follows by sort of aligning the dot, which is the composition operator in Haskell. So you read from bottom to top. So we first sort, then we apply an algorithm called map adjacent, and then we're applying the section that flips the minus so that we take the difference between those two elements and then just taking the minimum from that list. So I think at the break, someone was talking to me about one of the problems with these algorithms is that they aren't easily composable, and that presents sort of issues. And you can see here that when you have composition baked into the language, it makes it a lot simpler to read and to use, in my opinion. And so this is what it ends up looking like if we have the list 1, 4, 2. You sort it, you get 1, 2, 4. Then you take the difference between the adjacent elements, you get 1, 2, and then the minimum is 1. So now we get to our first point in this two-part talk where we are going to show some C++20 ranges code. And before I do that, I want to point out that in C++20, there's been 12 range adapters approved. Those are the ones on the left. I also make use of some range v3 algorithms that have not made it into the standard yet, but I didn't want to just use the 12 here. So if you see zip, group by, or tail, those are currently not in C++20, but hopefully some version of them will be in a future version of C++. So this is the equivalent version of the code that we were just solving using the adjacent difference, minute element, and sort. So here, we pipe our vector to RV, which stands for range is view. That changes our vector into a range, and you need to feed the range action sort a view or a range. So you can't pipe a vector to an action. You need to pipe a range to an action. So you can sort of ignore the first line, and at that point we get into our algorithmic. So we first sort, we then apply a function called adjacent transform, which is basically adjacent difference, but it doesn't have a default operation. I think it's more clearly named this way, and we pass it minus, and then we take the minimum. So the HS is just basically a namespace that I created in which we define minimum. So minimum is just making use of range v3's make pipeable. And so the point here is that you can't use the range-based algorithms that come with C++20 by default with the piping operator that comes with C++20. In order to do that, you have to basically wrap those algorithms in the ranges : make pipeable. So that's how you get your minimum, and this is how you get your adjacent transform. So this is pretty noisy, so I'm going to gray out what's not important. And the content of our algorithm, our adjacent transform, is here. So I've talked about this before. We are zipping with our tail. That's the equivalent of our transform reduce, where we pass it the 0 to n-1 and the 1 to n. So we've zipped, and the two parameters for our zip are the original range and then the tail of that range. And because zip is a lazy function, it's going to stop as soon as it gets to the end of one of the lists, which is going to be tail, which is the shorter of the two. And then in transform, it's basically going to take the list or the range of tuples, which is 2 elements at a time. I destructure those elements in that tuple into A and B, and then you just perform the binary operation on A and B. So this is going to be the start of a small digression, which talks about a feature that I really, really want in C++, which is quite common in other functional programming languages, and it is getting rid of the following. I think it's silly that I have to spend a whole line destructuring the contents of this tuple when I could just do it in the parameter list of the lambda. So here, I want to be able to use structured bindings in the parameter list of my lambda, so I don't need to spend a whole line on it in the previous solution. And there is actually a proposal out there, 0931R0, which proposes this, structured bindings with polymorphic lambdas. I'm not really going to talk about this standard at all, but just know that when you start to use composable algorithms in the C++20 and future standards library, or I guess it's just part of, yeah, it is a library, you're going to be able to make use of zip, which is going to necessitate the need for some sort of language feature, in my opinion, that enables you to not spend whole lines doing this. And we look at this, and then we move on to our next example. And when I was preparing for this talk, I realized that in Simon's code, he actually does basically the same thing, but he does it in the following piece of code, basically. So tuple, we have very poor support for tuple in our language and library. And so in order to get access into our tuple, you either have to do what I did, which was using C++17 structure bindings to name those basically values, or to use the get, angle, insert the index that you want, and angle on your tuple. So if we had this feature, Simon would have been able to use the same sort of destructuring in the parameter list of his lambda there. So that's the end of that digression, and it's the start of another digression, which is taking a look at what Ivan Kucic said in a recent talk that he gave at ACCU just at the beginning of this year.
So let's see a simple example. We want to count all the repeated occurrences, consecutive repeats of a character. Usually, in functional programming languages, you would do this by pairing using the original array, then use its tail, and then you have pairs of letters. For each pair, you just calculate, check, are they the same? Are they not the same, etc. And then you just need to sum everything. Conceptually, these are 3 completely different operations. Pairing with another collection, then iterating through all the elements and doing the transform, or as usually it's called in Haskell map, and then you do the accumulation to count how many characters have been repeated. In C++, we have a completely obvious algorithm for doing this, which is called, completely as expected, inner product. So when you see the name inner product, this is immediately what comes to your mind, counting the adjacent occurrences of a character, right? Because inner product is just that. So the inner product is a really cool example that you should never use, obviously, because this wouldn't fit the Phil Wadler quote. Now we do have the transform reduce, which sounds much nicer, and transform reduce could be fitted for this. But the problem is a little bit bigger than just the name. we have 3 different operations, but since we have the iterators and iterators are not easily composable, this couldn't have been just 3 different algorithms. This needs to be a single algorithm that is a composition of the previous 3. So what can be done to remedy this?
So if you want to see what you can do about that, you're going to have to go watch the rest of the talk. But this clip was mind-blowing for me. One, because I watched it a week before the very first time I gave this talk, and I basically have the exact same code in my talk, and I was like, huh, how did we have the exact same idea? Until I learned later that this Zipdale sort of what you get in the form of inner product in C++ is a very, very common idiom in other languages. But more so, there's 3 really important things that Ivan says here. The first one is that inner product, it's a really cool example that you should never use because he's in the party of thinking that it's a very, very poorly named algorithm for most of the use cases that you're going to want to use this sort of zip transform reduce pattern. The second thing that he says is that transform reduce sounds much nicer, but the problem is bigger than that. And the third thing that he says is that, he says a lot, but the main point is that iterators are not easily composable. And so as I've mentioned previously before, that this has been something that's coming up. When you start to push algorithms to their limits and really start to use them, you start to notice the lack of composability of the STL algorithms. And so we're going to come back full circle to this at the end of the talk. And you've sort of seen how C++20 ranges already in the last example, how it's starting to solve that composability problem of the STL algorithms. So here is the STL solution of the problem that he talked about in his video right now, or just now. So that was counting the adjacent equal elements. So similar to our find the minimum difference between all elements, we are basically going to make use of the adjacent difference function and then perform a count if on all of the differences calculated from that adjacent difference function. So note once again that we are starting at the second element because the first element is not actually a difference, it's just the initial value of our initial vector v. And this is the Haskell version. I've actually given this or shown this example in a lightning talk that you can find on YouTube. And this just shows how basically how easy it is to write STL algorithms in Haskell. So we can basically define countif just by composing length and filter. And adjacent difference is just the generic algorithm map adjacent using the minus binary operation. And then when we compose those 2 algorithms together, count if, whenever count if is equal to 0, that's when we know the adjacent elements are equal. And with adjacent difference, we basically get our answer. This is an example of how it would work if you had 1, 1, 0, 0, 2, 2, 3. You can definitely see that there are 3 adjacent equal elements. If we perform the adjacent difference, we're going to get 0, 1, 0, negative 2. This is calculating the difference between the adjacent elements. And whenever we have 0, we know that the elements that are adjacent to each other are equal. And so once again, here is a C++20 ranges version of that. We're making use of the adjacent transform algorithm that I showed earlier, and also now this count-if algorithm that's just basically counting whenever the transformed range has a true Boolean. And the count-if, once again, is just basically a wrapper around the ranges version of the count-if, making use of the ranges : make pipeable. So that's the end of that digression. So this is the sort of end of the discussion about transform reduce. Once again, it's my favorite algorithm. If you're not completely digesting everything I'm saying, I would definitely go and take a look at the spec for this function and try and understand it. You would be surprised how often this algorithm comes up when you want to first transform 2 different data structures, and then at the end of the day, you end up with just a single sort of value. Transform reduce comes up all the time. There's a small note that I want to make about sort of Jonathan Beccara's really nice illustration. This transform in parentheses here should be up with inner product. Accumulate goes with reduce, and inner product goes with transform reduce. But I still think this diagram is incredibly good because it highlights the default operations. So once again, with inner product, you can see that plus and multiplies are the default operations that come with the inner product and transform reduce algorithms. So we've now covered accumulate, adjacent difference, inner product, iota, and reduce. We have one pre-C++ 11 algorithm to cover, and that's partial sum. So we're going to do that now. So there are 3 different sort of partial sum applications in my mind that I've come across. The first one is summing multiple subarrays, which we're going to quickly look at. The second one is combining partial sum with binary search, which I'm not going to cover in this talk. And the third one is one we're going to spend a little bit more time looking at, and that's basically changing the behavior of partial sum through the use of lambdas. So first, what does partial sum do? Here we have two different examples, two different vectors. The first one is just 5 elements that are all 1, and the second one is 5 elements that are 1, 2, 3, 4, 5. And partial sum basically calculates all the partial sums, so basically the sums up to a certain index of all the elements that it's seen up until that index. So when you have all 1s, the result is going to be 1 for the first index, 1 plus 1 for the second index, which is 2, 1 plus 1 plus 1 for the third index, which is 3. I think you get the point there. And for the second example, for the first element, it's going to be 1, and then the second will be 1 plus 2, which is 3, and then 1 plus 2 plus 3 is 6. So basically, it's similar to reduce, but it calculates all of the incremental results as well and outputs them into a vector or whatever data structure you are constructing. Does that make sense to everybody? Or should I spend a little bit more time? I see a couple nods. Jonathan shook his head. Oh no, okay. All right, so we'll move on. So the first example of where you can really utilize this is when you have multiple queries of basically summing up subarrays. So if you think naively, if you've got a big list of numbers and you need to know from time to time what's the sum between index 10 and index 40, well, every time you want to do one of those sums, it'd be a linear time calculation in the length of sort of the difference between the two indexes. And so if you had a bunch of those queries, you're going to end up with sort of quadratic time complexity, linear for each sum, and then you're going to have, however many sums that you have to do. However, if you create a temporary vector, which we're going to call u here, and we use partial sum to calculate sort of the storage that u is going to contain, anytime we want to query what's the sum between index I and index j, or here we have sort of a and b, you can basically just take the difference between the two elements in that partial sum vector, because that's a property of basically the partial sums, is that you can, in constant time, get the sum of a subarray from the array that you're trying to get your sums from. So this is a really, really useful technique if you ever run into this problem. It turns a quadratic time complexity piece of code into a linear time complexity piece of code. So the other application of partial sum is going to be covered by this final problem here. So this is a LeetCode problem, if those of you who are familiar with this website. And it states, given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it is able to trap after raining. So basically, we have this range which is represented by the black cubes. And the question is asking, imagine that that blue stuff is not there, which represents the rain. If it were to rain, how much water could this range trap? And that is basically anytime you have sort of columns, you can get rain up to the minimum of the 2 columns on either side. So we're going to look at this problem, a simplified version of this problem, where we assume that the maximum of the range is at the very end. So we don't need to worry about finding the maximum yet. We'll come back to that afterwards. So this is a visualization of the problem where the maximum is at the end. And basically, we are starting at the left-hand side, and we are going to do a single pass where basically we keep track of the maximum column we've seen so far. And then at every column, we're going to check, is there a difference between the maximum we've seen so far and the current column height? And that difference, if there is any, is going to be the rain that that column can trap. So that's going to basically end up with the following. You have a basically trap unit of 1 rain in the second column. At that point, our maximum that we've seen is 2. Then when we get to the 4th column, we're going to reset our maximum to be 4. And then when we move to the 5th and 6th, we're going to trap 2 units of rain and 1 unit of rain, respectively. Does that make sense to everybody? We sort of do a single pass, and we keep track of the maximum, and then we just end up with the total amount of trapped rain at the end. So what does this look like imperatively? So at the top of our solution solve, we've got our vector v, which represents our range. Then we're going to initialize 2 local variables, m and answer. M is going to be the maximum we've seen so far, which we're just going to set to be equal to the first element in our vector. And answer is going to be the total rain that we've collected, and that's going to be equal to 0. So then we have a range-based for loop. We do what we said we were going to do, reset the maximum so far to be equal to the maximum of our current element and the max that we've seen at this point. And then we do a plus equals to our answer, which is the total amount of rain that we've seen. Anytime there's that difference, we are able to capture that rain, and at the end of our range-based for loop, we have our full answer. So how can we solve this making use of our STL algorithm partial sum? So here, we have our vector v once again, And then we have our vector u. U is going to be the white plus the blue that we saw on our previous slide. So right now, the vector v, that represents the white range. U will be white plus blue. Partial sum, we've overloaded. So the default operation that comes with partial sum is plus. In this example, it's max. So instead of partial sum, effectively, we have partial max. So we're not calculating the incremental sum of all the elements we've seen so far. We're calculating the incremental maximum that we've seen so far. And with this vector that we've output to u, we can now do a transform reduce, where basically we're taking u, subtracting v from it, so it's basically white plus blue minus white, and that gives us blue, and then we just need to sum all of our blue units of rain up. Does that make sense to everybody? I see half nods and everyone else not nodding. And so there's a similar optimization that we can make to this code that we made earlier, and that's that a property of a partial max applied vector is going to be that the element on the right is always greater than the element on the left. So we can once again swap the ranges that we're passing and then use stud minus instead of our custom lambda there. And note that I have put max into a custom function object. UFO stands for useful function object that you can find on my GitHub page. So this is a very clean solution using two algorithms, partial sum and transform reduce. Now, some of you might be thinking, similar to when we saw accumulate and when we saw inner product, that partial sum is no longer a good name for this algorithm because we're not summing, we're maxing. Introducing inclusive scan. Inclusive scan, once again, is the C++ 17 revamped version of partial sum. You might be thinking, why are we calling it scan? Scan is actually the more common name for what in C++ we call partial sum. Scan was first coined in the APL language, and in Haskell and almost every single functional programming language, this is referred to as either scan. So in Haskell, it's scan and scan1. I believe in other languages, it's scan and pre-scan. So inclusive scan basically starts at the first element. There's a sibling algorithm to this called exclusive scan that starts with an initial value. So basically, you're going to end up with one more element in your final range when using exclusive scan compared to inclusive scan. So it may not seem like the best name in the world, but if you compare it to sort of the prior art of other languages, it's a very, very good name. And so going back to the original problem, we were solving a simplified one where the maximum was at the end of our range. So what if the maximum is not at the end? Well, how can we modify this solution to basically solve for the full problem? So what's the first thing that we need to do in order to solve the full problem? Does anybody know? So someone just yelled it out, max element. So we need to identify where the maximum is in our range. So we've stored that in our iterator now. And so what's the second thing we need to do? A little louder? Calculate both sides. Yes. So our first inclusive scan, we no longer want to do to the end. We want to do it to the maximum. So I'm not sure if you can see that change there. Basically, we were previously doing it to the end. Now we're doing it to the maximum. And finally, we need to take care of basically the second half of our array, which we can do by just making call to another inclusive scan, but using reverse iterators and starting from the end. And there's just a tiny little piece of code there, the rev, which is a templated alias in order to turn our basic iterator into a reverse iterator. And so just like that, we've now solved the full problem. So I think partial sum or inclusive scan is also an extremely, extremely useful algorithm. And I think because we call it partial sum in C++, it doesn't get enough attention, as much attention as it deserves, similar to how std accumulate is not called full or reduce. But when you start to really understand the behavior of std reduce and std inclusive scan, you start to find them everywhere. And so I think as like an exercise, going home and really trying to understand inclusive scan and how you can customize it with different binary operations is really important. So now we have covered all but 2 of the 11 numeric algorithms. And at this point, we're going to sort of pause and we're going to switch to covering something called the algorithm intuition table. So this is a different way that I have sort of developed to think about the algorithms that we've covered so far. So this is what the algorithm intuition table looks like at the beginning. We're going to change it a little bit over the next few slides. We have our accumulate and reduce, our inner product and transform reduce, partial sum inclusive scan, exclusive scan, adjacent reduce, and iota. And I have categorized them by sort of 3 properties: the number of indexes that we're looking at, whether or not the algorithm has an accumulator, and whether or not the algorithm is either a reduce type of operation or a transform type of operation. And so hopefully with the reduce transform thing, I'm not like reinventing something in category theory that I'm not aware of at the moment. But if I am, I apologize. So if we take a look at accumulate, how many indexes does accumulate look at a time? And I should note that index refers to which column. If you're looking at 2 different ranges or 2 different like vectors, but you're only looking at 1 index across those 2 vectors at a time, that still counts as 1 index. And that's what sort of the asterisk in the second row means, is that it can also have a 2-range sort of version. But so back to accumulate and reduce, we have 1 index because we're only looking at 1 index at a time. Because we're doing a fold operation, we definitely have an accumulator value. And at the end of the day, obviously, accumulate slash reduce is a reduce type of algorithm. If we skip to partial sum once again looks at 1 index at a time. And does it have an accumulator value? Yes, it does, because we are bringing either the partial max or the partial sum as we go through this algorithm. And what type of algorithm is it? At the end of the day, we end up with a vector of values, not just a single value. So this is a transform type of algorithm. And so we have this for all of our algorithms. One of the algorithms that we're going to add to this table immediately is the pattern that we've seen now twice, and that's what I'm calling adjacent reduce. It's a wrapper around either inner product or transform reduce that basically internalizes the zip tail functionality. So here we are basically making a call to inner product. It could be transform reduce as well. And then we are passing it the 0 to n-1 elements of our range, and then the 1 to n elements of the same range. And we can call this adjacent reduce. Now we're basically ignoring in the name of the algorithm the transform and the zip, and we are looking at adjacent elements because you only have 1 range, and you're just looking at adjacent elements at a time, and you're applying a binary operation basically to transform, and then another binary operation to reduce these values down. So we add this, and the properties for this is that we're looking at 2 indexes at a time. It does have an accumulator value because we're reducing at the end of the day, and at the end of the day, it's a reduce. So we're now going to solve a problem using this table. So it might not be clear at this point what's the usefulness of sort of creating this table and separating these algorithms based on their properties. The usefulness is this. You can solve problems using this table. So here's a code forces problem. I'm not going to read the whole thing. It boils down to, given a string of 1s and 0s, return true if the longest contiguous substring of equal elements is greater than 7. So basically what that means is here we have 2 examples. In the first example, the longest contiguous substring of equal characters is 2, the 2 zeros. And that's not greater than 7, so we return false. In the second example, I think we have like 8 or 9 zeros in a row, so that's going to be greater than 7, so we return true. So it's a pretty simple problem. So how do we solve this using the algorithm intuition table? So first, I guess let's look at the imperative solution. So here we've got 2 local variables, max player and current players. We initialize those both to 1 because we know at least there's going to be 1 character in a row that's the same. Then we have a indexed for loop that starts at the second element, and then on the first line of our for loop, we basically check is the current element the same as the previous element? If it is, we increment the number of players in a row that are the same. If not, we reset it back to 1. And then on the second line, we reset max players to be equal to the maximum of the maximum players in a row that we've seen so far and the current number of players that we've seen so far. So whenever we're in the midst of what is going to end up being the maximum contiguous substring, we'll end up resetting max players, but all other times max players will just be being reset back to itself. So how can we utilize the algorithm intuition table to solve this problem by using one of our algorithms? Well, so first, how many indexes are we looking at in this problem at a time? 2. So it has to be one of the algorithms that uses 2 indexes. Do we have an accumulator value needed to solve this? Yes, because we need both the max players and the current players as we go through the algorithm. And is this a reduce or a transform at the end of the day? It's a reduce because we're just returning a Boolean. So the answer, we solve this using adjacent reduce. So what does that look like? So here the same code. Because it's a little bit noisy, I'm going to replace max player and cur player with just MP and CP. and it makes it a little bit easier to read. So adjacent reduce, once again, remember this is a wrapper around inner product / transform reduce that zips basically the 0 to n minus 1 and 1 to n. And so that means we've got two binary operations happening here. The one on the last line is the transform operation. So here we're using stud equal to. That basically is going to check, are our adjacent elements equal to each other? And it's going to transform that either into a true or a false. And then our second binary operation is the lambda that we have in our first sort of binary operation after the make pair. So we initialize the accumulated values that we're bringing with us to both be 1. The first in that pair is our max number of players, and the second in that pair is our current number of players. Then we basically, in our parameter list, spell out, I could have used auto and type inference, but I think it's easier to see. The pair of two integers is our accumulator values, and the second parameter is the equal that we get from the transformed equal to adjacent elements. And then we use destructuring, structure bindings on the first line of our lambda to name MP and CP, our max players and current players. We have the same code now. If those two players are equal, if the Boolean is equal, then we increment CP by 1. Otherwise, we reset CP to 1. And then at the end of that, we return our pair. And once again, the first element in our pair is our maximum. So we have to set it to maximum of our max players and current players. And then the current players for the current number of players that we have equal in a row. So this works, although it's a bit noisy. And I think this is just supposed to be illustrative of, I don't think without the table, I would have ever recognized that I could have solved that problem using an algorithm like adjacent reduce. This is the Haskell version of solving this problem, which is why I love Haskell so much. So the way this works, group, once again, you work from the bottom to the top. Group is an algorithm that creates, if given a string or a list, it creates a list of lists or a list of strings that has all of the equal characters or elements in these sublists. So given the string 001, 001, it gives you a list of strings of just the equal characters. You map the length, so then take the length of each of those substrings, then take the maximum of those lengths, and then you have a section here which is basically just a very short lambda that is basically going to be a unary operator that checks if the maximum is greater than or equal to 7. So Haskell is very, very beautiful. But we can go to our C++20 solution, and it looks very, very similar to Haskell. And this code makes me extremely happy compared to this solution, which there is a certain amount of elegance and beauty to it in the fact that we can make use of an algorithm. But compared to this C++20 code, I think it pales in comparison. So unlike Haskell code, we read from top to bottom here. So once again, we're making use of the group by equal to, and that does the same thing that Haskell's group does, sort of. And then we transform those sub-strings, or sub-ranges, I guess, using the distance, which is the same thing as length. And then we reduce that down to the maximum of those values, and then we test, is it greater than or equal to 7? So this should get you extremely excited about C++20 ranges. Currently, group by is not in C++20, and we have to do a little bit of boilerplate to be able to pipe the maximum and GTE functions. But this actually is the start of a digression of a blog post that recently was posted in August by Barry Revzin, and he referenced my original talk where I had this example before I had the C++20 code. And he basically showed that this would be the way to solve it using C++20 ranges. Unfortunately, this doesn't work, though, because you can see that it's using the ranges version of any of. And those are not pipeable in the ranges C++20 pipe syntax. You have to wrap the any of. And so this is just, it's a really, really good article. It focuses on a proposal that he had originally called uniform function call syntax that would have solved this problem, but that failed. I wasn't there, but I'm not sure if it was a glorious fire or a small fire. But it doesn't look like we're getting UFCS in C++. But he then goes to propose, not in a paper, but just as an idea, this operator, which I recently learned is actually referred to as the pizza operator, because it looks like a slice of pizza. But this would enable us basically to, without writing any boilerplate, pipe basically other ranges as the first parameter of our range algorithms that come with C++20. So if you're interested in this stuff, definitely go check out Barry's article. End of that digression, and back to our algorithm intuition table. So we've got 6 algorithms here, or 7 algorithms if you include IOTA. I just put it there because I felt bad for IOTA. But let's fill in a few more. So can anyone tell me which algorithm satisfies these properties? 2 indexes, it doesn't need an accumulator value, and it is a reduce ESC algorithm. There's an asterisk next to it, which I'll explain in a sec. Anybody? Yes, Jonathan Bacara with the answer. Adjacent find. So adjacent find looks at 2 indexes at a time, the adjacent ones. It doesn't need an accumulative value because it's just basically returning true or false, or it's actually going to return an iterator, but ultimately it's looking for whether the predicate that you've passed it is satisfied, the default predicate is equal to, and at the end of the day it's a reduce. The asterisk there is because it's a shortcutting reduce. So it's not actually a reduce in the sense that it's going to map over or reduce over the full data structure. It's going to short circuit as soon as the predicate that you've passed it satisfies or returns true. The next one, can anyone name indexes viewed 1? The star meaning that there could be 1 range or 2 range, but it's still only 1 index. It doesn't need an accumulator value, and it transforms. Yes, so 20 people got chocolates there. So yes, this was an easy one. Very well named, if I do say so myself. Who can get this one? Indexes viewed 1, accumulator no, and reduce asterisk. Yes, someone in the front row or second row, I believe. It is find. And at that point, we've almost completed the 8 possible different combinations of our 3 properties, 2 to the power of 3, because they're binary properties. But as I was looking at this table, I started to get a little bit upset because I realized that one of these algorithms is just really, really poorly named, and I sort of alluded to it on a previous slide. Who has seen this piece of code, generating Fibonacci numbers using the transform algorithm? I see a couple hands, 3, 4 hands. So it is a, I guess, less well-known fact that you can generate Fibonacci numbers using the transform algorithm by basically initializing the first couple values, or all of the values, to 1, and then passing the 2 ranges that you might need to be basically the first element to the second last, or the third last element, and then your second range is the first element, and you don't need to specify the end because it's just going to go off of the first range, and your output iterator is going to start at the third element. So you're going to have 1, 1, and then you're going to start adding the 2 previous numbers. And you just need to pass the binary operation plus, and you're good to go. At C++ Now 2019, several months ago, I was talking with Ben Dean, and without him having seen my talk, he mentioned, have you seen the code, or did you know that you can generate Fibonacci numbers with adjacent difference? Which should really upset you. This is basically a specialized version of transform. But you'd never know it because difference is in the title. And here we're overloading the default binary operation that comes with adjacent difference with stud plus, and then basically doing the same thing. The adjacent part is taken care of. We don't need to pass it 2 ranges. Question? Okay. But so when Ben told me this, I sort of freaked out a little bit, and I went back to my slides and I added this slide, and then I also added this slide where I basically point out that adjacent difference is entirely the wrong name for this algorithm. It should be adjacent transform. Yes. Yeah. So there's a question from Chris. Okay, yeah, so the comment from Christabella is that there is actually a subtle difference between a generic adjacent transform and adjacent difference, and that is that it swaps the parameters from the input range. So if you are given your A parameter on the left, B parameter, it swaps them before it applies the binary operation. Is that correct? Yeah. So that is a good thing to point out. I would argue that it's still a bad name. We should call it adjacent transform, and we should provide a facility in the language similar to Haskell's flip in order to take care of when you want to do that. Because I think we miss out on the opportunity to use the adjacent difference algorithm in tons of different use cases that you'd never think of just because the difference word is in the algorithm name. and it completely obfuscates the semantics of the algorithm due to that. So yes, adjacent difference is, I think, a terrible name that we should probably rename. And this is where I sort of make the point that it's extremely important to know the default operations that come with these algorithms, and to know that you can completely override these operations. So with inner product and transform reduce, they come with plus and multiply, but you can override them to do a plethora, basically an infinite number of things. Similar with adjacent find. The default binary operation that comes with adjacent find is equal to. So it's basically looking for two elements next to each other that are equal to each other. But you can do a ton of different things with adjacent find. Basically, there's an algorithm in the STL called isSortedUntil. You could implement that in terms of adjacent find by overloading the default binary operation with less than. And so it's just really important to basically acknowledge these default operations. So there's one last algorithm that we're missing here, and that's the one that satisfies these basically criteria. 2 indexes, an accumulator value, and transform. I was very sad when I went to go look and try and find this, and I couldn't, and so I just went and wrote it myself. So I'm calling this adjacent inclusive scan. There could be several different varieties of this algorithm. This is a sample implementation of this. We're not going to walk through it, but basically note that we've got basically a previous element, an accumulator, and there's a special treatment we have to use for the first element, and we're applying our binary operations 1 and 2 in our while loop, and at the very end, we're just returning O, which is the output iterator. However, and sorry, this is an example use case of it where basically we are summing adjacent elements whenever the adjacent elements are equal to each other. But when I went back to this list, we sort of had avoided covering transform inclusive scan and transform inclusive scan. And I thought, oh wait, I just implemented an algorithm that is there. That's what I said the last time I gave this talk, which went up on YouTube, and then someone on YouTube commented the following. So I've replaced temporarily adjacent inclusive scan with transform inclusive scan, but I got this comment which says transform inclusive scan takes just a unary operator for its transform part. So if we go and take a look once again at CPP reference, and we take a look at all of the overloads of this function, for the transform operation, it's always a unary operation. So we don't actually have the parity with inner product and transform reduce and transform because we're missing the binary operation for transforming. So actually, my adjacent inclusive scan is valid because that doesn't currently exist. And my guess is that either myself or someone in the future is going to write a proposal to fill out those missing overloads. And the very last comment I want to make is that hopefully by now it's become very clear that the base STL algorithms, the sort of non-range versions, are not composable. And we also run into this problem where certain algorithms, you know, we have copy and we have copy if. We have partition and stable partition. We have these prefixes and these suffixes that we can append to create new algorithms. And here I've sort of identified 3 properties, but what if we want to start adding properties and like filling this out? And so some of you might be aware that certain algorithms there's an _n version for, but we don't have that _n version for all of the algorithms. If we run into this sort of combinatorial problem where these base algorithms, in order to create the new ones, you basically have to define a whole new one that internally is doing some sort of faux composition. So it's a real problem that when you really start to utilize algorithms, you're going to hit this wall, which is why C++20 ranges is going to be so awesome. So there's one last problem that I want to solve in the last couple of minutes that I have here. Some of you may have noticed at the start of my talks, the 2 title slides have this font. Does anyone know what board game this is from? Scrabble is unanimously from the crowd. So Scrabble is one of my favorite board games. And I never really realized this, but if you take a look at sort of one of the operations that takes place when you're scoring in Scrabble, and for those of you that don't know, Scrabble is like a crossword building game. So you place words on the board, and each of the letters has a tile value, and then with the multipliers on the board, you basically calculate each word score. So if we were to do this with the word algorithm, and we were to place it on this place on the board. So when there's nothing, it's a multiplier of 1. When there's a triple letter score, believe it or not, there's a multiplier of 3. Can anyone tell me what algorithm it is to basically calculate the score of this word? Inner product and transform reduce. So if we have a vector for W, which is our word, and each of the elements of our word is the tile value, and we have a T, which is the multiplier for that tile, is a transform reduce. And And it might be hard to believe, but this shows up everywhere, which is why I love the algorithm so much. I love the fact that it's named transform reduce, because previously when people argue that, oh, inner product's not a good name, they can't say that about transform reduce, in my opinion. It's a generically named version of inner product that is incredibly useful. So before we conclude, I just want to highlight, I'm sure many of you know, but I think a lot of people on YouTube might not know about these other conferences. All of these conferences record their talks online. And I think that's fantastic because this is my first conference. And before this, I was still able to watch a lot of the content. So thank you to all the audio folks and the film crew in the back for putting this online. And thank you to the conference for funding this. Podcasts, if you're interested in, the two main C++ ones, CppCast and CppChat, but also LambdaCast and Functional Geekery are incredibly good. Functional Geekery is just amazing. They have people from different programming languages, Simon Peyton-Jones from Haskell. They have fantastic people, and the conversations are amazing. You definitely should all read these. They're out on the table. And subscribe, follow me on Twitter. And to conclude, algorithms are awesome and fun, especially transform reduce and all the other algorithms that we mentioned. Know the default operations of the algorithms that they come with, but know that you can override these default operations and really leverage the power of these algorithms. For example, adjacent difference. Would I actually recommend using that in production? No, but maybe write your own algorithm that's called adjacent transform that wraps adjacent difference that then makes your code readable. And that's a great talk that Marshall gave in the past, where he talks about you don't always have to rely on the STL algorithms. You can start to write your own, and he shows you how in his talk, so you should go watch that. And last but not least, C++20 ranges and composable algorithms are coming, and you should get very excited for those. So thank you. Any questions? 4 chocolates. No?
How much do you think the bad naming comes from them having default parameters that specify parts of the implementation? The parts of the behavior?
Probably 95%. So the question is how, or I guess it was already recorded, how much does the bad naming come from the default operations? I think it's almost entirely due to that. And maybe I didn't articulate that, but I would have preferred a STL algorithm library that didn't come with default operations. But that is sort of the trade-off you get between functional programming and sort of imperative programming. I believe probably the motivation for providing default operations is they make the algorithms easier to use. And for a lot of the use cases, accumulate is what you want to do. Like probably, I'm not sure if summing up numbers is something that you do more often than multiplying numbers, but a lot of the default operations I think are good choices. However, sometimes they come with the obfuscating what the actual sort of abstract semantics that the algorithms are doing, and then it means that you're not going to use them in other cases. And I would prefer requiring the developer to have like a little bit of a higher cognitive load to think about, oh, how do I get it to do this? Like I prefer the APL, what they call a plus reduction. They don't have sum, they've got to reduce, and then they have a bunch of binary operations, and you always have to combine a binary operation with your reduce in order to get your algorithm. I prefer having to explicitly think about that, and I prefer that cognitive load being with the programmer, but I definitely know like different programming communities and different people are going to have different thoughts on that. So I think it's personal to a certain extent, but that's just my preference.
Since I appear to be the only one asking questions, I'll go for the next
Sure.
one. I noticed you skated past std accumulate and the common problem of std accumulate double with a 0 passed to it.
Yes. That's a great point. Is the default, or sorry, the return value of a std accumulate and std reduce is dictated or set by the value that you pass as the third parameter. So when you pass it 2 iterators and then your initial value, if you're summing up doubles or floats and you pass it in integer literal, it's going to do a bunch of truncation. So you have to be very, very careful with the initial value that you provide, accumulate and reduce. So yes, that's a great point.
So some of these algorithms with outputs that alias are depending on in-order execution. And many of these algorithms have generalizations or overloads, parts of the overload set that don't guarantee in-order execution. Do you think that's a code smell?
I plan on giving another talk that really highlights the difference between this, because I think I'm not 100% sure that the examples that I gave in part 1 of this talk, where I showed the count and the any of using std reduce, I think those might be broken, but you can still make use of transform reduce to do the transform of your values into a Boolean or whatever you're doing at the end of the day. And so to answer your question, I'm sort of going off on a tangent. I don't think it's a code smell. I think having a very comprehensive understanding of the difference between the non-parallel and the parallel algorithms is paramount. And not having that, a lack of that comprehensive understanding is going to lead to bugs. But I think that most developers in the world don't think in parallel currently. But in a decade, I think that is probably going to be changing. And that's why a talk really delineating the difference between a non-parallel and a parallel algorithm and what exactly can be used when you need that associativity and that commutativity. I think that's extremely important. So is it a code smell? No. Is it something, or so if the definition of code smell is we should be very careful and make sure that there's no mistakes there, then it is a code smell. But when I think code smell, I think sort of like anti-pattern and things we should avoid. But I think it is definitely going to be something in code reviews that should be paid attention to. And if that's what you mean by code smell, then yeah, I completely agree. And so yeah, I think we're a couple minutes over here. So with that, I think we're done. Thank you so much for coming.